Hey, hello everybody. I'm going to teach you about something um, really useful for examining networks that have some sort of physical interpretation, specifically networks that kind of describe um, maps between places. So, for our example today, we'll have um, a three node network. So we'll have nodes 1, 2, and 3. And you can think of these as if they're cities with roads connecting them. But let's say that there's only a road from 1 to 3 and 1 to 2, and vice versa. It's undirected. But there's no road from 2 to 3. And we want to quantify the general accessibility of this network as well as the individual relative accessibilities of each of the nodes. So here's how to do that. We're going to first make our adjacency matrix. So you all caught on to this very quickly, so I'm just going to kind of blaze through it. We have a 0, so we're putting zeros on the diagonal now. I got this wrong in the previous video, and I had to correct it, but zeros go on the diagonal instead of ones. And then 1 is connected to 2, so we'll put a 1 here, and 1's connected to 3, so we'll put a 1 there. Then 2 is connected to 1, so we'll put a 1 here, and 2, we'll put a 0 on the diagonal for itself, and then it's not connected to 3, so we'll put a 0 there as well. And then for 3, 3 is connected to 1, but 3 is not connected to 2, and it's a 0 for itself. And this will be our matrix. Now, to compute Gould's accessibility index, we have to go through a lot of steps. This is going to get very complicated, and I in no way will expect you to memorize it. So I recommend taking thorough notes on this process because it is in some ways a total mess, but it comes out with a really useful measurement. So here's what we have to do first. Let's call this matrix A, and the first step that we have to take is define matrix B, and matrix B is equal to matrix A plus the identity matrix. Now, what's the identity matrix? The identity matrix, so I'm just going to rewrite A right here. The identity matrix is just a matrix that has ones on the diagonal and zeros everywhere else. Shoot, 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 shoot. And so what we get when we do this is the same matrix, but with ones on the diagonal instead of zeros. So we're kind of back to where we were when I made the mistake, where we have the same matrix, but we're now putting ones on the diagonals. And now, what we're going to do, something that people will call me crazy for including in this course, is we're going to find, so this is step 1. Step 2, we're going to find the eigenvectors of the B matrix. Eigenvalues of the B matrix. So eigenvalues are a thing from linear algebra, which is also sometimes called matrixology, the study of matrices. And they have a lot of different interpretations, but in this case, we're going to take the biggest one, the biggest eigenvalue, and our interpretation of that is that it's going to be a measurement of the accessibility of the network. Okay, so the first thing that we have to do is find, the first thing that we have to do is we have to take B, and we have to subtract a variable from each of the elements on the diagonal. So this is going to become, instead of looking like this, we're going to have 1 minus, and we'll call the variable lambda. just out of convention. 1 minus lambda, 1, 1, 1, 1 minus lambda, 0, 1, 0, 1 minus lambda. And I'm going to put these bars here. And what these bars indicate is that we're going to take the determinant of this matrix. I'm sorry about all the new words. If you don't want to memorize the new words, don't bother. Or just determine net. If you want, you can just pay attention to the process. So again, long and drawn out, but it's going to be very important that you trust the process. So what this means is we're going to first take this element. So we're going to focus on the top row here. Look at the first element of the top row. So 1 minus lambda. Let's write 1 minus lambda. And then we're going to multiply 1 minus lambda by, so we're on this corner. We're going to take this square on the opposite corner. So we're jumping from here to here, and we're going to multiply it by the product of these two things minus the product of these two things. So we'll do times 1 minus lambda times 1 minus lambda, this times this, minus 0 times 0. Okay, now we're going to hop over to this element of the first row, and we're going to subtract. The next term we're going to be subtracting, because we go add, subtract, add. Again, complete madness, but trust the process. We're subtracting 1 times, and now we're going to ignore this column, and we're going to do the same thing, but we're going to multiply this by the product of this and the product of that and that. So 1 times 1 minus lambda, so 1 minus lambda, and then minus 0 times 1. Okay, and that's the second of 3 terms in this determinant. And now we'll do plus, so we're back to plus. We started with a plus and we did minus, plus. We're moving to this element, this 1, and we're going to multiply that by the product of these two minus the product of these two. So 1 times 1 minus 0 minus 1 minus lambda in parentheses times 1, this times this. And that's everything. But we can simplify this very, very thoroughly, of course. So I'm going to do that down here. I'm just going to tilt the camera a little bit to make sure we can see. So this is going to be equal to 1 minus lambda, this should be in parentheses too, minus lambda, and then times 1 minus lambda, it's 1 minus lambda. That's what this becomes, because this is just a minus 0, so we're doing 1 minus all these things. Okay, and now we'll do minus, and then this is just minus a 1 minus lambda, because we have 1 times 1 times 1 minus lambda minus 0. So at the end of the day, that's just 1 minus lambda. And then we have this term, which is 1 times 0, so that's a 1, minus 1 minus lambda, so we're doing another minus 1 minus lambda. Okay, so to recap so far, we found our B matrix by putting ones on the diagonals, and then we subtracted these lambdas from the diagonal elements, and now we're taking this determinant, which involved multiplying each of these top row elements by the cross products of the corresponding squares below. So it was like this times this or this times this minus this, and this times that minus that, and so on. With this plus minus plus scheme, again, don't, so yeah, plus minus plus. I'm just going to put that there as an extra reminder. Again, do not try to memorize this by any means. But at the end of the day, we have this determinant, and what we need to do is we need to set it equal to 0, and then solve for lambda, figure out what lambda has to be if this equals 0, and that will be our eigenvalue. And we'll get a couple solutions, but the biggest one is the one that we're interested in. So first of all, what I'm going to do is I'm going to modify this expression slightly by multiplying together these two 1 minus lambdas, and I'm going to combine these into just a minus 2, just like minus 2 of these. So this becomes, so we'll have 1, we're factoring this, so we'll have 1 minus 2 lambda plus lambda squared. That's what you get when you FOIL this out. And then still times 1 minus lambda, and then minus 2 minus lambda. That's just combining these two, minus lambda, minus 2 minus lambda, minus 2 times that. So now we have that, and what I'm going to do is I'm going to factor out these two 1 minus lambdas from each of the terms, and so what we'll have is 1 minus 2 lambda plus lambda squared minus 2 times 1 minus lambda. Right, so we're just taking this factor out of each term. And so this, and then this is just a term with everything being added or subtracted, and this we're just adding or subtracting another 2. So subtracting this 2 from this 1, what we get is this becomes minus 1 minus 2 lambda plus lambda squared times 1 minus lambda. And now this, as before, we must set equal to 0. And so now we have, from here we can find some solutions, because we know that these two things being multiplied together have to be equal to 0. And so that means that either this equals 0 or this equals 0. So I'm going to make some room over here. And I'm going to rewrite what I've got at the end up here. So we had, and I'm going to reverse the order of the terms in this section here. So I'm going to rewrite it as lambda squared minus 2 lambda minus 1 times 1 minus lambda equals 0. Okay, so from this term, we have that one solution is lambda equals 1, right? That's one solution, because if lambda equals 1, this term equals 0, 0 times anything is 0. So we've got one. And the other the other solutions we'll get from setting this equal to 0. So, the way we would solve this, the way I would like to solve it, is just by using the quadratic formula. It might be factorable, but it won't always be factorable, so I prefer just to use the formula immediately, because I don't think it takes that long, and most of us had to memorize it in high school anyway. So lambda equals, okay, so negative b, so 2, plus or minus the square root of b squared, 4, minus 4ac, so that's 4 times 1 times negative 1, so that's plus 4. Right, is b squared minus 4 times plus 1 times negative 1, so yeah, it's plus 4. All over 2a, so all over 2. And so this equals 1 plus or minus the square root of 8 over 2. The square root of 8 is equal to 2 times the square root of 2. So 1 plus or minus 2, or yeah, 2 square root of 2. 2. So our solutions are 1 plus or minus the square root of 2. So we've got lambda equals 1, we've got lambda equals 1 plus square root of 2, and lambda equals 1 minus square root of 2. And so our dominant eigenvalue is the largest of the three, which is 1 plus square root of 2, and so this is equal to our GAI, or our Gould's accessibility index. Okay, so the one last thing that I want to set up here after we've found our Gould accessibility index is, so this represents the we had our network, and it looked something like this, where we had I guess 1 was going to both 2 and 3, and this represents the overall accessibility of the entire network, just the average accessibility of all of it. But I want to just set up the way that we would find the individual accessibilities of each node in the network. And so the way we do that is as follows, and I won't actually do it, but I'll set it up. So I'm just going to erase this bottom piece. Okay, and so what we're going to do is we're going to take that matrix from before, the one that was B minus the the lambdas, and so we had 1 minus lambda, 1 1 1 1 minus lambda. Sorry, I'm just gonna put this in here. 0, then 1 0 1 minus lambda. Okay. And then we're going to go ahead and plug in, I'm just going to make some room here. We're going to plug in our dominant eigenvalue. So plug in largest, plug in largest lambda. And so our largest lambda was 1 plus root 2. So what we're going to get is, we're going to get minus root 2 for each of these elements, because 1 minus 1 plus root 2 is just going to be negative root 2 on all of those. So minus root 2, 1, 0, 1 minus root 2, 0, 1, 0, and minus root 2. Okay, and then what we need to do is we need to multiply this by a vector. So say we have a vector that's like x1, x2, and x3, and we want this to be equal to 0. The multiplication of this matrix by this vector. So the way this works is we're just going to, and this actually is not just 0, but a column of 0, 0, 0. So if this is freaking you out, it's much, much simpler than it looks. All we do is we take these 3 x's and we multiply it by each row. So this top row just becomes an equation on its own. It becomes negative root 2 x1 plus 1 times x2 plus 0 times x3 equals 0. So you see how I did that? I just took x1, x2, x3, multiplied it by these 3 things, added them together, they equal 0. That's one component of this matrix vector equation here. It's just this equation with these 3 variables, x1, x2, x3. And so if I do that again with the next row, it's 1 x1 bloop, bloop, minus root 2 x2 plus 0 x3 equals 0. And then for the last row, it's 1 x1 there, and then plus 0 x2 minus root 2 x3, that equals 0. And so now we've got a system of 3 equations and 3 unknowns. You'd see that a lot of these terms would drop out because they just equal 0. So like this, you don't even have to write any of these terms that are multiplied by a 0. And then this is actually quite relatively easy to solve. And what you do is you just substitute. You'd solve for one of them, substitute into the rest of them, and that's how you would carry out the rest of this. And then the values of x1, x2, and x3 would precisely be the relative accessibilities of node 1, node 2, and node 3. And so that is very useful as well. So if you already forget how we started this whole mess, then don't worry too much. We're going to go through some examples of this in class, and you'll get a little bit more comfortable with it, I think. You might be saying, Ben, stop huffing all the burnt bike fumes, but I really think that you'll be able to do this at the end, even if it seems super overwhelming right now. So check out the self-quiz. It won't expect too much of you. and then we'll whip through this in class, and it's going to be very exciting. So I'll see you all then.